It starts with a solid metal workpiece clamped securely on the rotary table. The HSTM 150S2 is equipped with a dynamic snubber system that stabilizes the blade during cutting. This is critical when working on thin-walled sections prone to vibration. The tool approaches with precision, cutting complex airfoil curves while maintaining micron-level accuracy. Before any material is removed, the machine calibrates itself with warm-up cycles to stabilize thermal conditions. Multi-axis interpolation lets the spindle pivot and sweep across contours, trimming excess material while preserving exact geometry. At this stage, chip evacuation and coolant flow are tightly controlled to prevent heat distortion. The snubber moves in sync with the spindle, absorbing micro-vibrations and ensuring surface consistency. It's a quiet battle between steel and stress, and this machine wins every time. Tool paths are generated from CAD CAM programs, optimized for tool life and feed efficiency. The machine adjusts feed rates based on depth and curvature, enabling aggressive material removal without losing dimensional tolerance. Every tool is measured and verified before mounting to avoid even the smallest misalignment. Midway through, inspection probes measure surface accuracy and position, feeding real-time data back to the control system. If any deviation is detected, offsets are corrected automatically. This feedback loop minimizes scrap and rework. The operator monitors everything from a touchscreen panel, reviewing data as the machine works. Near the end of the cycle, finishing tools apply a fine pass over critical surfaces, like the snubber mount or root area. These final touches determine how the blade will perform under high thermal and mechanical loads. Once the cycle finishes, detailed reports are generated and logged for traceability and certification. Watching this operation is mesmerizing. Tight clearances, smooth motion, perfect repeatability. The result isn't just a machined part, it's a piece of trust, ready to face thousands of hours inside a jet engine. Instead of repeated hammering, a hydraulic press with a hemispherical die gradually presses the metal into shape. The upper and lower dies match in contour, shaping both faces of the head simultaneously. The compression is slow and powerful, forcing the metal to flow evenly across the die cavity. Each forming step is timed to maintain pressure long enough for full die contact. Engineers monitor the operation closely, ensuring temperature remains consistent to prevent cracking or uneven deformation. The curvature of the dies concentrates pressure at the center first, then distributes it outward. Each press cycle is calculated to control grain flow and avoid trap stress. Advanced simulations often guide the sequence, predicting metal movement and potential failure zones. During this stage, visual cues, like scale pattern and color gradient, help workers judge metal behavior in real time. As the final form appears, what was once a thick raw disc now takes on its precise, domed shape. The forged head is then removed and set aside to cool gradually. Watching this transformation isn't just technical, it's elemental: fire, force, and steel working together with deliberate control. 3. Gallo-torneria, lavorazioni meccaniche e tornitura 117. https://www.youtube.com/watch?v equals YHPWFI-AG-NVC. Every cut and contour in this shop is all about mechanical mastery. Raw metal bars are loaded onto CNC turning machines, where advanced software controls every axis for flawless results. As the bar spins, cutting tools carve out precise geometries, turning, facing, and grooving each section in rapid sequence. When the design demands it, CNC milling heads step in, creating complex profiles and detailed features with sharp accuracy. Each finished part is checked with digital gauges, guaranteeing tight tolerances and perfect finishes. The technicians here have serious skill, and their attention to detail is obvious in every product that leaves the floor. Watching these machines at work is a reminder of how far modern machining has come. This facility doesn't just make parts, it powers what moves the world. At Varroc, components like polymer panels, transmission shafts, crankshafts, switches, and high-precision engine valves are manufactured under one roof. Advanced automation controls every step, while quality checks are embedded throughout the process. Lighting systems, including OLED and laser beams, are assembled with tight tolerances for top-tier brands like Tesla and Audi. Multiple sites handle production across different regions, allowing machines and engineers to specialize in key systems. Each assembly line is tailored for specific product families, helping reduce setup times and streamline output. What really stands out? The speed and consistency. It's impressive to watch how each system runs with efficiency and discipline, turning bold innovation into everyday reliability. Steel frames for rolling mill stands are welded edge by edge, molten seams flash, sparks crackle, and each joint locks into industrial strength unity. This is where tight radius tube bending becomes effortless. The JUTEC B-Edge System 5000 handles diameters from 6 to 50 millimeters with hydraulic force and mechanical precision. Its modular bending head switches between left and right bends quickly, perfect for complex geometries. Tool changes are seamless thanks to plug-in bending dies. Watching this compact unit in action, fast setup, smooth motion, sharp angles, it's clear why it excels in production settings. You can almost feel the torque as each bend forms cleanly. It's efficient, flexible, and surprisingly powerful for its size. It's just a blade, until you see what goes into it. At this facility in France, industrial saw blades are made with a mix of high-precision equipment and skilled hands. It begins with raw steel sheets delivered by suppliers. Though they look flat, each sheet must undergo leveling to remove coil-induced curves and internal stress. This step ensures the stamblatt, the core body of the blade, is truly flat and stable. At this stage, even the tiniest distortion can affect how the blade performs later. The leveled sheet enters the laser cutting station, where nesting software maximizes material usage. Each profile is cut with precision. Any imperfections are detected immediately. After cutting, residual stress from the heat must be removed to prevent deformation. So the blanks are stacked, pressed, and undergo thermal treatment to bring tension back to a neutral state. No part is left to chance. This process is closely controlled to ensure proper planarity and concentricity. After heat treatment, each blank is pre-tensioned using two specialized rollers. This gives the blade stability during rotation at high speeds, adapted to specific applications. Without this controlled tension, the blade would warp under centrifugal force. Now comes a step few expect: hand straightening. Each blade is inspected, then manually corrected for runout and long axis stability. If a blade can't be aligned, it's discarded. Flatness and balance are absolutely non-negotiable. Next, carbide teeth are sorted, oriented, and soldered onto the rim using automated brazing systems. Misplaced teeth are instantly rejected. Then the brazed area is sandblasted to remove heat marks and oxidation. Only clean, smooth surfaces proceed. It's fascinating how much precision is demanded, even for parts that are just millimeters wide. Afterward, each blade is scanned to verify correct tooth count and positioning. Any flaw, any misalignment, back it goes. Then, the teeth are ground. Specialized grinding machines shape the tips, trapezoid, alternate bevel, or other forms based on use: plastic, wood, metal, or composites. Each angle matters. Hook angles, clearance angles, radial geometry, everything is measured. Then the entire surface is polished. This isn't just for shine. A smooth surface prevents imbalance and ensures the blade runs quietly and evenly. Even the polishing has a role in reducing vibration during high-speed operation. Runout is then tested with a high-sensitivity measuring system. The tolerance? Less than 1/10 of a millimeter. Only blades that pass move on to laser marking. Here, all essential specs are added: diameter, bore size, number of teeth, max RPM, and production codes. If problems ever occur in the field, each blade can be traced. Finally, the blade is labeled, packed, and shipped. But production doesn't stop here. For special models like PCD, polycrystalline diamond, additional steps are taken. These ultra-hard tips are eroded, not ground, because diamonds can't be cut by traditional means. PCD blades last 10 to 20 times longer than carbide and are made for high-demand applications. Even with all this machinery, each blade passes through multiple hands and strict controls. It's no exaggeration to say, a proper saw blade isn't just manufactured, it's built with intention, one detail at a time. Heavy rail components demand serious machining power. The Gickamil R, a gantry-type milling center, takes on switch points and frogs with continuous 4-axis motion. Its head can rotate through 38 indexed positions, covering a plus or minus 90 degrees range, allowing seamless access to multiple surfaces without repositioning. Watching the machine glide over massive steel parts while holding tight tolerances is incredibly satisfying. Each pass removes material with purpose, shaping intricate curves and profiles required for complex rail junctions. The gantry structure adds rigidity, reducing vibration even during aggressive cuts. It's not just the size that's impressive, it's the control. Seeing that head pivot in fluid motion reminds you just how far modern milling technology has come. After the wire rods are formed and cooled, the next challenge begins, handling tons of coiled steel with precision. First, each coil is transferred vertically to a compression unit. Massive hydraulic plungers descend to press the loops downward, reducing the coil height and tightening the layers. This not only saves space, but stabilizes the bundle for storage and transport. The compression cycle is timed automatically, with pressure sensors controlling how much force is applied to each bundle. Once compressed, the coil remains centered between steel columns as it's moved through the next stages. Vertical lifts and rollers raise and align the coil for inspection and labeling. The entire unit rotates and shifts to prepare for offloading, with guides ensuring it stays locked in place. A mechanical lifter moves the coil horizontally onto a rail conveyor. These steel tracks carry the coil to the loading bay, where it joins dozens of others, lined up and ready for shipment. Shock absorbers along the conveyor line help reduce vibration during coil movement, protecting both equipment and material integrity. Throughout the process, operators monitor alignment and make manual adjustments if necessary, an essential touch in such a highly automated environment. Despite the size and weight, the system flows smoothly. You can see the raw weight of the material, yet everything moves with rhythm and control. It's not just about force, it's about balance, coordination, and making sure every steel coil leaves the floor ready for its next destination. At the Lincoln plant in the UK, a 16,000-ton screw press forges massive crankshafts, wheels, and axles with extraordinary force. Heated steel billets, weighing up to 350 kilos and 2 meters long, are shaped in seconds under closed die forging. Before impact, each piece is precisely centered by mass and geometry. Magnetic particle inspection checks for internal flaws, then full machining cuts them to final dimensions. Watching this, it's hard not to feel impressed. This isn't just heavy machinery in motion, it's controlled destruction turned into mechanical art. Disassembling a massive gear isn't just heavy work, it demands accuracy at every step. It's first lifted out using overhead cranes and heavy-duty chains. After disassembly, technicians mount the core onto a large CNC lathe to machine worn sections. For press-fit components, localized flame heating expands the bore to allow removal. Reassembly begins with precise alignment, torque-controlled bolts, and careful handling of gear mesh. Each segment demands intense focus. This is craftsmanship on an industrial scale. Watching these teams move around such massive parts with skill and coordination is seriously impressive. It's loud, it's complex, and it keeps the mechanical heart of heavy industry alive. Molten brass flows like liquid gold through this extrusion facility in Jamnagar, Gujarat. First, raw materials are melted and refined in high-temperature furnaces. The molten alloy is then cast into billets and cooled. These billets are reheated and pushed through dies to form solid or hollow rods. Every extrusion is cooled, straightened, and cut to length. Workers inspect dimensions, while machines remove surface oxidation for a smooth, clean finish. It's impressive how much consistency they achieve with such a reactive metal. Final rods are bundled and weighed before shipment. Watching the transformation feels almost hypnotic. But make no mistake, this is all about precision, not beauty. In this city of brass, the process never sleeps, and neither does the demand.